Okay, so now that you've checked in, we're going to switch gears and go from kind of the elementary what happens in equilibrium, that's kind of the basic concept, and move more to the advanced side of equilibrium, which is explaining why it happens. And for most students, I would say, this is slightly more difficult only because it just requires more thought into why something occurs. It's not as simple as just memorizing shifting opposite. So I want you to move beyond that kind of lower level, it can shift opposite when I increase something, towards trying to explain why that occurs. Because in the end, we want to know why it happens, not just what happens. We want to have an explanation for it. So the way we're going to approach it is through the rates of reactions. Because equilibrium is all about rate. If you speed up a reaction, you speed up its rate, we're going to see a shift. And it's actually relative to the rates of all the reactions. So for example, in my first section up here, the reactants going to products, I've increased by show of this red arrow, larger red arrow, I've increased the rate of the forward reaction. So this would be an example of increasing the rate of the forward reaction. So if I have a really large arrow pointed in the right direction, and I don't have as large of an arrow, so in other words my rate of my reverse reaction isn't as fast, then I'm going to see an overall shift to the right because the forward reaction is pumping out products to a greater extent than the reverse reaction is putting back the reactants. So if I initially produce a disturbance that increases the rate of the forward reaction, I'm going to see it shift to the right because that rate of the forward reaction speeds up. Also, I can do the same thing with the products. If I add something that increases the rate of the reverse reaction, I can speed up that reaction of products to reactants, and I can see it shift to the left as we start producing more reactants in the process. Conversely, I can decrease the rate of a reaction. So if my forward reaction decreases in rate, you see this small tiny little red arrow. If I decrease the rate of that forward reaction, now it's not spitting out products as fast as the reverse reaction is spitting out reactants. So decreasing the rate of the forward reaction actually shows us a shift to the left, because now the reverse reaction is faster than the forward. Or conversely, if I slow down the rate of the reverse reaction, so I decrease the rate of the reverse, whoops, you can't see that a little bit there. If I decrease the rate of the reverse, then we see the forward reaction going at its normal rate, and the reverse reaction now is much slower, so therefore we see an overall shift to the right because now it's making more products than are forming reactants. So we're going to try to approach every question from a why does it happen angle. And to do that, we're going to need to explain it with three requirements hit. First, what changes for the forward rate? Does it get faster, slower, or does it stay the same? Secondly, what happens to the reverse rate? Does it get faster, slower, or stay the same? And then lastly, as a result, if the forward gets faster and the reverse doesn't change, what is the net result? What do we actually see? We see a shift to which direction, and what do we see as colors? Okay. Now, I want you to remember that this is all about collisions. So the faster the reaction rate is, the more collision, in other words, the more collisions that happen, the more that reaction is going to point in the direction of the shift of equilibrium. So in other words, if I add something that causes more collisions in the reactants, well then that forward rate is going to speed up and it's going to point us towards the products. It's going to make more of those products overall. Let me go through as many examples as I can go through, and we'll see if you can get it. Hopefully we can get through all of the second example here. So example 2, this is part A. This is a yellow reaction. We've got HCl and oxygen reacting to make chlorine gas and water. Notice we have a liquid here, water, and we have the rest are gases. This is an endothermic reaction, so heat is a reactant. Okay, so first of all, let's balance, right? We always balance our reactions. So our reaction here, 4 HCl's, 2 waters, 2 chlorines. Okay, so our disturbance is going to be that we're going to add more oxygen gas. So which component of this reaction is affected by having more oxygen gas around? Well, I hope you can see that since O2 is a reactant, and we're adding more of it, we're going to increase the concentration of the O2 gas, the oxygen gas. So where does that appear? Is that in the forward reaction, right, the reactants, or is that in the reverse reaction, the products? Again, it's in the reactant side. So if I increase the concentration of the reactants, I'm going to increase the rate of the forward reaction. So the forward reaction increases. Let's go to the reverse reaction. Does the rate of the reverse reaction change? Well, O2 is not found in the reverse reaction. So adding more of it doesn't speed up or slow down that reaction because it doesn't depend on O2. So it stays the same. Therefore, if we have an increase in the right, so increase in the forward direction, and no change in the reverse, we see an overall shift to the right, and in this case we'd see more of a yellow-green color maybe. Okay? So again, I'm analyzing this by which component was affected, which rate changes, and therefore which shift do we see. Let's try another example. This is adding more Cl2. This is example B. Again, I'm going to get my reaction to be balanced. So adding more Cl2, which component am I affecting? In this case, Cl2 is a product, so I'm going to affect the Cl2 in this reaction. Which rate, does the rate of the forward reaction increase, decrease, or stay the same? Well, the forward reaction doesn't care about Cl2 because it's not part of that reaction, so it will stay the same. How about the rate of the reverse? Well, the rate of the reverse will change because now having more Cl2 increases its concentration. So now the reverse reaction is going to speed up, so it gets faster. So if we see no change to the forward and an increased rate of our reverse, we see it point and shift to the left. And therefore we'd see less of that yellowish color or yet less of that greenish color. Okay, now we're going to move on to example C, which is adding more H2O liquid. So which component is affected? Again, let's go to the balancing, right? Which component is affected? Well, H2O is a liquid. So when we say which one is affected, we're talking about which one will affect the rate. All of these are gases. None of these are aqueous. So adding more water doesn't affect anything. We just have more of it there. So it's not going to speed up the rate of any reaction. The rate of our forward doesn't even use water, so it wouldn't change anyway. The rate of our reverse actually doesn't change because adding more water doesn't increase its concentration, so it doesn't speed up that reaction, that reverse rate. So there is no direction of shift, and therefore the color stays exactly the same. So adding something that is not speeding up the reaction will not change the position of the equilibrium. It might mean that we have more water around that can react with chlorine, so the reaction will last longer. Might be able to get more out of the reaction, but it doesn't change the position of the equilibrium. We won't see a shift in the position. Okay, let's go on to example D. So let's decrease the volume of the container. Again, go back to our balancing. We've got 4 HCl gases, 1 O2 gas, making 2 liquid waters and 2 Cl2s. So what is affected by a change in the volume of the container? I hope that you got from the example we did earlier that any gases that are present are going to be affected by this, because now that they have a smaller space to work in, their concentrations are going to increase. So let's look at what happens to the rate of the forward reaction. Well, the forward reaction has gases. There are 5 of them. 5 gases, that's going to be a large increase in the rate because their concentrations are now going to increase quite a bit because they're a lot closer together. There's a lot more likelihood that they're going to hit each other. The reverse reaction also includes gases, so when we change their volume, we're also going to increase their ability to hit each other, but they're not going to increase as much. So yes, they're getting closer together, but the relative distance away that they are as a result of this smaller volume is not as big of a deal as how close together these 5 gases are now going to be. It increases the likelihood that these 5 gases will collide to a greater extent than the likelihood that the chlorine gases will collide, even though both increase. And because the forward reaction is going to increase to a greater extent than the reverse, we're going to see a shift to the right, and we're going to see that greenish yellow color. Okay, let's move on to example E. Again, we'll do the balancing. So I'm going to heat up the system. Which component is affected when I heat up, when I change the temperature of the system? Hopefully you can see that the temperature, the heat is written on the left-hand side. However, we know that temperature affects the rate of reaction. We know if we increase the temperature, it speeds up the reaction. So in reality, both rates of reaction, all the reactions that are happening in this system will increase in rate because we're heating it up. But the reaction that uses heat is going to be specifically targeted. So that is in the forward reaction. So we would actually see a great increase in the rate of this reaction because now we're supplying that extra activation energy for that reaction to go. And since this is endothermic, this reaction must require a lot of energy to run. So adding more energy will speed up the rate of this forward reaction quite a bit. The reverse reaction doesn't require energy to start it, right? It will go back on its own pretty easily because there's no heat term written here. But it will increase in rate. It just won't increase as greatly as the forward reaction will increase. So overall, we'll see a faster rate to the right, somewhat faster rate to the left, but overall we see a shift to the right because the faster reaction is the forward reaction. And we'd see that greenish color appear again. Okay, let's try example F. Let's cool the system. Again, same deal, let's balance. When we cool the system, same deal. We're going to affect all the reactions, but the reaction that uses heat is going to be affected to the greater extent. The forward reaction requires heat to begin. It's an endothermic reaction. It must mean that there's a lot of energy required for that forward reaction. If that's the case, if I cool the reaction down, that's going to impact the forward direction a lot. An incredible amount. It's going to decrease by a ton because now we don't have that activation energy necessary for the reaction to occur. The reverse reaction can still happen. It's going to go slower because that rate's going to slow down as the temperature lowers. So it will decrease as well, but it doesn't require as much activation energy as the forward must. Therefore, it's not going to be as affected as much. So because the forward slows down a ton and the reverse slows down but not as much, we're going to see an overall shift to the left, as now the reverse reaction is actually going to be faster than the forward. And we're going to see that yellowish, light yellow color appear, because we're going to be getting rid of this yellow-green chlorine. Okay, last one. This one's a doozy. What happens if I add H2 gas and a spark to the chamber? So again, let's balance. The question is, which component is affected? So what is H2 going to affect? Let's first start with, is H2 part of the forward reaction? No. Is H2 part of the reverse reaction? No. So is adding H2 going to increase the concentration of anything in this reaction? The answer is no. So if it's not going to increase the concentration of anything in this reaction, then we want to explore the option that maybe it decreases the concentration of something in the reaction. Is H2 and a spark, the spark must be to provide a little bit of activation energy. Is H2 going to react with HCl, with O2, with H2O, or with Cl2? I hope that you can see, or hope that you're familiar with, the reaction between hydrogen and oxygen. It's actually the oxygen that would be affected, because hydrogen and oxygen react together. That was like the rocket lab we did last semester. You spark a mixture of hydrogen and oxygen, you're going to get the two to react together and make water. So these oxygen and hydrogen are going to react together. So what's going to happen to the O2? Well, now that it's sitting there in the form of water, right, which is a liquid, doesn't affect the rate of a reaction, the O2 goes down. So the forward reaction is going to slow down suddenly because there's not going to be much oxygen around. The reverse reaction doesn't change because it's not affected by the removal of oxygen. Oxygen's not part of that reaction. So it stays the same. So we see a decrease in the forward rate. So it's a small arrow going to the right, and our reverse reaction doesn't change. The regular arrow going to the left. So we see a shift to the left and therefore less yellow color. Okay, so if there's any time left in your class, I'd like you to try example 3. See if you can go through these 7 different disturbances and determine what happens for each. Which direction does it shift? And then your reason should include not just what happens, it shifts to the right or left or no change, but Why does it happen? What happens to the rates of reactions? Work with your partner. Good luck.